Okay, so let's take a look at this one here. We want to graph the function r squared equals 9 cosine theta. Um, and so what I need to do to graph this, even on Nismos, it will not graph implicit equations for polar coordinates. We'll do that for x and y, but it will not for polar. So I will have to actually rewrite this equation as r equals plus or minus 3 cosine of theta. And I do need both because r could be positive or negative in this equation. So this is one we could again graph by hand, right? We could graph this by hand, looking at a few points, but it's much more straightforward, I think, to do this with technology. I really want to show you the kind of graph we get. Again, the usefulness of using these parameters. Okay. So here we are. This is the actual graph. It's almost kind of an infinity symbol in a sense. Notice how it gets really flattened and down here on these two parts. Let's just look at the one side for now. This is the positive 3 square root of theta. And let's just look at the graph. Oh, I forgot to put my parameter a in for the graph there on both of those. So let's now look at this as a starts to range a little bigger. So zoom out just a little more here. So as we start out, again, cosine is close to 1. So when you have the 3 in front, 3 times cosine of 1, of course, it starts there at a radius of 3 away from 0. And then cosine keeps getting smaller until eventually cosine reaches 0 when we hit pi over 2. So what's going to happen here? We swing out. It gets big for a while. Not gets big. You're getting closer to 0 every time, but does it kind of slowly at first, and then really accelerates those last few points. Now, what's going to happen is I keep graphing. You say, well, where's the graph? Well, remember, when we get into the second quadrant angles, cosine's negative. Square root of cosine's not going to produce anything. So there's no graph there. And that's going to continue as we pass pi. We're passing in through the third quadrant. And it's not going to be until we're in the fourth quadrant that the graph now resumes and starts graphing again. And then once we reach 2 pi, there we are. And of course, the same thing's happening here, except these angles are negative. So what's going to happen is the negative radius, of course, everything's going to be the other way, right? So what would have been here is reflected through on the negative one. And then you can see the graph. Now nothing for a while until finally we get back to the fourth quadrant. And now you have the fourth quadrant stuff here on the one, reflected through on the other. And we have this this graph, which kind of looks like circles, except they're not really circles because they're really flat over here on the y-axis. Okay, so that's just one example of a graph that we can graph with that. Again, we could have probably done that one by hand, but it still would have taken some work. Okay, we can see a lot more from the graph. So this next one here has a really interesting graph. As we're looking at e to the sine theta minus 2 cosine of 4 theta. So I started out intentionally with the graph not showing up because I want you to see what happens. It's a really cool math graph here. So we start swinging out, right, hitting some values. Here we are again, hitting some more values. This graph's kind of looping in on itself until eventually you get this shape. And so we've actually graphed a butterfly, really. That's how I was kind of think of this one. We have a butterfly. R equals E sine theta minus 2 cosine of 4 theta. Just a really cool looking thing where, again, we're graphing what amounts into a butterfly. Now it's what amounts into a butterfly. Now there are a few places where the graph is really staying positive, right here through most of the second quadrant, until you get to this one little place here where it does loop. Again, this would have been graphed as I reach pi there over here, but you can see it's negative, so it's being reflected through a little bit of negative, and then it's back to positive again for most of the time until I reach this point right here, where again it would have been coming through. Now it's negative, so it's coming back through. So you actually see it intersects on itself, which is again something polar graphs can do. They have XY plane places where the graph crosses, but it never actually crosses at the same values of r and theta. Okay, it never actually crosses the same value of theta. Okay, so kind of a pretty cool little graph there as we graph a butterfly. Okay, the last one I want to look at here is a graph of something like r equals 2 sine theta plus 1. 2 sine theta plus 1. Here we actually have a graph again that loops on itself. Not as complicated as the butterfly we looked at a moment ago. But what's actually happening here is the graph for a while, you're just taking on positive values. Until we reach a point here, I think in this example it happens at 7 pi over 6, where that graph of r equals 2x plus 1 would actually take on negative values now. And so it would have normally been graphed down here, but it's looped inside on itself. And so you actually have this inner loop. This is called a limmason with an inner loop. You can see how that inner loop comes about if we looked at the absolute value of that graph. Here we are, we hit 0. Absolute value, of course, this is where it would have been falling. Right? So you have it like that, kind of weird looking graph. But the other one, of course, this loop is all negative values, so it's reflected back inside. And so the graph loops in on itself. Again, that's called a limmason. If those values are equal, of course, you get your heart shape that you saw before. If the number being added on is bigger, then you get this kind of more of a blobby shape, where it kind of blobbies out. And that's also called a limmason, except it doesn't have the loop. Okay, so the cardioid is kind of the special one, where it comes in at kind of that sharp point. And of course, if that number is less than 1, then you have the loop inside. It's less than 2 and less than 2. The more less than 2 it is, the bigger your loop inside. You can see there with 0.1, it's really big loop inside. But if I did 1.9, you can almost not see that loop. It's there. It's just really, really small. Okay. All right, so that's just a little bit more about some graphs and using technology. We're going to look at one more question. Here, and we're going to use technology to kind of verify our result.